This is a good question to look into some of the fundamentals over here for this chapter, for this topic, that is. So we have an object of mass 20 grams. So we have an object of mass 20 grams and is suspended by a string of 60 centimeter. So it is held with a string of 60 centimeter. Keeping the string taut, the ball describes an horizontal circle of radius 10 centimeter. Means it is going round this way, and this radius happens to be 10 centimeter. So basically, if I take this up, paste it over here, we have that basically. And all of this is suspended somewhere over here, and attached to this is a thread, and this happens to be 60 centimeter. Okay, what else should I tell? And that would be it. So this is okay. We'll assume quite a few things over here, that this object is kind of small, a dot basically, and this length we'll consider as 60 centimeter. Okay, so I can erase this and write this as 10 centimeter, and this is 90 degree, and this is moving in horizontal direction. Okay, so let's look at the free body diagram of the object. Oh yeah, mass is 20 by 1000 kg. I think, yeah, that's it. We're looking at figuring out angular speed. So the object is getting pulled in one particular direction. We don't know what is that angle as of now. And what else is acting on it? Yes, your gravity is acting on it. So that would be m into g. In this case, it would be 20 into, or let me not make the diagram complicated as of now. Okay, so first thing is, who is supporting this? The string is supporting this, right? So the string is supporting this, and let us represent the force with this amount. And yes, it by default will be, how much will this force be? It has to be mg. There's no other option. And this will be how much, that we need to figure it out. So if I consider this as theta, you have to do a bit of math and figure it out. So this is the force along the string, and this is your force parallel to the horizontal or perpendicular to the, how do I take it as? So along the horizontal, okay, so string component along the horizontal, and this is force of string along the vertical. That we know it is mg. It has to be mg because it is stationary when it comes to the vertical. It's not going up or down. That's what I mean. That's what stationary means. In a one particular axis, that is y-axis, it's stationary. So it's neither going up or down. So we'll consider up and right as positive. Okay, so that's your free body diagram, and let's look at it, what is happening. So what is the goal over here? Well, we have to go to omega. But how do we go to omega with all of this? See, this is something that I just came up with, looking at or thinking about what is happening around, and so on and so forth, I didn't think too much. I just wrote what comes naturally to us by now. So we know quite a few things about object motion and free body diagram. I just did that. That's a better diagram. So I just did this. Now the question is, what is omega? How will we figure out omega? Well, we need to figure out acceleration. How will you figure out acceleration? And this where our force comes into picture. And this force is our string's force along the horizontal. That's it. That's how we'll figure out omega. So we have to figure out this basically. Let's start with that. Now, from figure, what can we tell? Think about it. Right? Applying. What will I apply? Newton's second law along vertical. So what we have here is right, and since it's not accelerating, what we have is f of s along the vertical minus m into g is equal to 0, as the object is moving along in a horizontal plane. As object is moving around horizontal plane and all of that, and so this is 0. So fs comma v is equal to mass is 20 by 1000 into 10. So 0 0 0 0 gets cancelled, and we have 0.2 Newton. So this is 0.2 Newton, right? Because it's a very small mass over here, so we just need a very small force. So with this, how will I figure out the horizontal component? How can I do that? For that, we have to go to the first diagram. Can you think how can we use the first diagram? If this is theta, okay, I have this as 60, this as 10. So what can I do? Yes, we can make use of cos theta. So from figure, so this is to do with theta. Theta is equal to adjacent, which is 10, and hypotenuse, which is 60. Sorry, cos theta is equal to 10 by 6. Theta is equal to cos inverse of 1 by 6, not 10 by 6, 1 by 6. Okay, so with this in hand, can I figure out this value? We can, right? So again, cos theta is also equal to, now we can figure out FSH. So from figure 2, we have cos theta is equal to force along the horizontal by force along the string. So the component FSH is what we are trying to figure out, and this is 0.2, and we have FSH is equal to 2 by 60, so 1 by 30, which is equal to 0.03 and all of that, 0.03 bar Newton. Okay, so we figured that out. What else? Next we can figure out AC. How will we do that? Well, we can make use of mass and we are done. So AC, so FSH is equal to your centripetal acceleration times of mass, and AC is equal to, this is 0.03 divided by approximately, this is 2 by 100. I never like to write in this manner, it's kind of confusing. This is the best way to go about. So this is 1.5 meter per second square. I hope I didn't do any silly mistake over there. And finally we have omega, which is omega square r is equal to AC, and this is 10 centimeter is 1.5 0, 0, 15. So 3 point something will be there. I mean, that would be the answer. 3.987 actually radian per second. Okay, let me see if I have done everything right. Okay, so let me have a look over here. So what we have is omega is what we are looking for, AC, FSH and all of that. Okay, 20 by 1000, 60 centimeter, 10. That's your basic scenario. Then I started with free body diagram. So we have a pull down of mg. So we need a component same magnitude as mg to keep the object in a horizontal plane basically, right? So they have to be equal and opposite. For that to happen, we need theta is, okay, wait, did I make theta wrong? Theta is sine, I think I got theta wrong. Cos theta is cos theta. No, wait. mg vertical, okay. And I found theta. FSV is this, not FS. Oi, okay. Just a second. Okay, so this is obviously wrong because we don't know FS. We know FSV. So we know we want horizontal. We're looking at vertical. So horizontal is adjacent. This is opposite. Vertical is opposite. And this is adjacent. Okay, my bad. What I did, I have to make use of vertical, which I know of. That is opposite to angle theta. FSH is adjacent. That's what I have written over here. And this is nothing but your 1 by tan theta, or if not cot theta. So in my calculate, I can take 1 by tan theta. So we need to figure out theta value over here. So cos inverse of 1 by 6. This is approximately 80.5 degree. So 1 divided by tan of 80.5 is okay, let me try this. 0.167, and so this will change actually. This everything will change. So this would be 0.167 into 2. 0.167 into 0.2. 0.0334 Newton. And now we have 0.334. I mean, approximate, if I do approximate, I'll end up with 3 over here. Not a good thing. Okay, let me just continue. 0.033 into 100 by 2. 65. This is 1 point. .65, and then we have 1.65. Alright, 16.5 root of 16.5 root of 16.5, 4.06 radian per second. Okay, wait, root of 16.5, yeah. Okay, so, quite a few bit of approximation, but point is I messed up basic trigonometry over here. One by tan, makes sense. 1 by tan value is big. Okay, now it's proper. So where was I? So applied over here, I found the vertical component, and then I found theta. And once I know theta, I can figure out any part of the triangle. Of course, we know one side, so we have to figure out the other side. So for your reference, you have to figure out the base. You know the height, you don't know the hypotenuse, you know the angle. This is 80.5 degree. This force is 0.2 Newton. We are trying to figure out this. That's all I did over here. So tan theta is opposite 0.2 by x. So if I interchange, x will be 0.2 divided by tan theta, and so the answer. So once I know the force, then I can figure out the acceleration. Once I know the centripetal acceleration, I'll be able to figure out the velocity, angular velocity over here. So the key takeaway here is, what I'm trying to expose you guys is, whenever you see any acceleration, there has to be a force. That's the whole chapter, right? So we have to have a force, and that force comes from this string as of now, right? And that force is what we are using to figure out omega. So I just wanted to introduce indirectly that we have the cos also taken into consideration in this topic, and that is nothing but your force, and this force can occur in many forms. It can be gravitational pull, it can be magnetic pull, it can be a thread, it can be a road banking, friction basically. Then what else? It can be a glass, surface. So yeah, quite a few things are the normal force, right? Quite a few things are there. So for now, you guys can pause, do copy everything, and we'll do a lot more numericals to understand this concept better.